Introduction. See those holes on honeycomb.
Yeah, how beautifully the bees make honeycomb.
Have you noticed the holes in that? They're in pattern.
Hey, yes, they form a pattern.
In nature we can find so many things with patterns.
Things like,
Things like pine cone.
wow, I never noticed this pattern before.
Our maths teacher taught us about one of these patterns in which succeeding terms are obtained by adding a fixed number to the preceding terms.
That sounds interesting. I also want to know about such type of patterns.
Okay, I'll tell you more about it. Objectives. At the end of this lesson, you'll be able to explain arithmetic progression, define term and common difference, write the general form of AP, find the nth term of given AP, find the sum of first n terms of the given AP, and solve examples related to AP. Definitions 1. In nature, many things follow a certain pattern, such as the seeds of a sunflower, the spirals on a pineapple, the pattern on cactus, and so on. Arithmetic progression is a study of one of such patterns. The arithmetic progression can also be called as arithmetic sequence. Before talking about arithmetic sequence, let us know what a sequence is. A sequence is a set of numbers that follow a pattern. We call each number in the sequence a term. Look at this example of sequence. This is the first term. This is the second. This is the third, and so on. An arithmetic progression is a list of numbers in which each term is obtained by adding a fixed number to the preceding term except the first term. This fixed number is called the common difference of the AP. Look at this sequence. We can see here that the common difference is 3. In general, we can write an arithmetic sequence like this: A plus D, A plus 2D, A plus 3D, and so on, where A is the first term and D is the difference between the terms, which is called the common difference. Definitions 2. Look at this example now. We can see that this sequence has a difference of 3 between each number. Therefore, A is equal to 1, the first term, and D is equal to 3, the common difference between terms. Let's form the sequence using A and D. We know AP is equal to A plus D, A plus 2D, A plus 3D, and so on. Substituting the value of A and D, we get 1, 1 plus 3, 1 plus 2 into 3, 1 plus 3 into 3, and so on, which gives the sequence 1, 4, 7, 10, and so on. There are two types of arithmetic progression: finite arithmetic progression and infinite arithmetic progression. The arithmetic progression having a finite number of terms, or which has a last term, is called finite arithmetic progression. And arithmetic progression having infinite number of terms, or which does not have a last term, is called infinite arithmetic progression. Here are some examples of infinite arithmetic progressions. Look at this sequence now. Can you tell its common difference? Yes, you're right. Its common difference is minus 3. In general, for an AP, A1, A2, and so on till AN, we have D as AK plus 1 minus AK, where AK plus 1 and AK are the K plus 1th and the kth terms respectively. Example. Let us now solve some examples. Observe this sequence. We will find out whether these numbers form AP or not. Here A1 is minus 3, A2 is 3, A3 is minus 3, and so on. Now let's find A2 minus A1, which is equal to 3 minus minus 3, which is equal to 3 plus 3, which is 6. Also, A3 minus A2 is equal to minus 3 minus 3, which is minus 6, as A2 minus A1 is not equal to A3 minus A2. The given sequence is not an arithmetic progression. Nth term of an AP. If the initial term of an arithmetic progression is A1 and the common difference of successive numbers is D, then the nth term of the sequence is given by An is equal to A1 plus n minus 1 into D. We know that An is also called the general term of the AP. If there are m terms in the AP, then Am represents the last term, which is sometimes also denoted by L. Now by using the formula of nth term, let's find the 8th term of the given AP. Here A is equal to 2, D is equal to 7 minus 2, which is 5, and n is equal to 8. We know that An is equal to A plus n minus 1 D. So, A8 is equal to 2 plus 8 minus 1 into 5, which is equal to 2 plus 35, which equals 37. Therefore, the 8th term of the given AP is 37. Example. Find the sum of the first 40 terms of the AP, 2, 4, 6, so on. We can see that given series is an AP with first term A is equal to 2 and common difference D as 2. We have to find the sum of first 40 terms. So, n is equal to 40. We know that S is equal to n upon 2 into 2A plus n minus 1 into D. Hence, S40 is equal to 40 into 2 plus 40 minus 1 into 2 by 2, which is equal to 1640. So the sum of the first 40 terms of the AP is 1640. Find the sum of the first 1000 positive integers. Let S is equal to 1 plus 2 plus 3 plus so on plus 1000. Using the formula for the sum of the first n terms of an AP, we have Sn is equal to n upon 2 into A plus L. Substituting the value of n, we get S1000 is equal to 1000 upon 2 into 1 plus 1000. This is equal to 500 into 1001, which becomes 500. So the sum of the first 1000 positive integers is 500. Find the sum of first n positive integers. Let Sn is equal to 1 plus 2 plus 3 plus so on plus n. We can see that here A is equal to 1 and the last term L is n. Therefore, using the formula Sn is equal to n upon 2 into A plus L, we get Sn is equal to n into 1 plus n whole upon 2, or Sn is equal to n into n plus 1 whole upon 2. So, the sum of first n positive integers is Sn is equal to n into n plus 1 whole upon 2. Find the sum of first 19 terms of the AP whose nth term is 2n plus 1. As the nth term an is 2n plus 1, so first term a1 is equal to 2 into 1 plus 1 is equal to 3. Second term a2 is equal to 2 into 2 plus 1 is 5, so on. And 19th term is equal to 2 into 19 plus 1 is equal to 39. So the list of numbers we get is 3, 5, 7, so on, 39. Now to find S19, we have n as 19, a as 3, and L as 19. Therefore, S19 is equal to 19 upon 2 into 3 plus 39. This is equal to 19 upon 2 into 42, which equals 19 into 21, which is equal to 399. Hence, the sum of first 19 terms of the given AP is 399. Did you know? The nth term of an AP is the difference of the sum to first n terms and the sum to first n minus 1 terms of it, that is, an is equal to Sn minus Sn minus 1. Summary. Let us summarize what we have learned. An arithmetic progression AP is a list of numbers in which each term is obtained by adding a fixed number d to the preceding term, except the first term. The fixed number d is called the common difference. The general form of an AP is a plus d, a plus 2d, a plus 3d, and so on. In an AP with first term a and common difference d, the nth term, or the general term, is given by an is equal to a plus n minus 1 into d. The sum of the first n terms of an AP is given by s is equal to n upon 2 into 2a plus n minus 1 into d. If L is the last term of the finite AP, say the nth term, then the sum of all terms of the AP is given by s is equal to n upon 2 into a plus L. Objectives. At the end of this lesson, you'll be able to explain quadratic equation, find solution of a quadratic equation by factorization, find solution of a quadratic equation by completing the square, explain the nature of roots. Quadratic equations. An example of a quadratic equation is The name quadratic comes from quad, meaning square, because the variable gets squared, like x square. It is also called an equation of degree 2, because of the 2 on the x. The standard form of a quadratic equation looks like this. ax square plus bx plus c is equal to 0. The letters a, b and c are coefficients. They can have any value except that a cannot be 0. The letter x is the variable or unknown. Example on quadratic equations. We will now check whether the given equation is a quadratic equation or not. Solution. Here, LHS is equal to x into 3x plus 4 is equal to 3x square plus 4x. So, x into 3x plus 4 equals x square plus 1 can be written as 3x square plus 4x is equal to x square plus 5. Therefore, we get 2x square plus 4x minus 5 is equal to 0. It is of the form ax square plus bx plus c is equal to 0. So, the given equation is a quadratic equation. Roots of quadratic equation. A real number alpha is called a root of the quadratic equation ax square plus bx plus c is equal to 0, where a is not equal to 0 if a alpha square plus b alpha plus c is equal to 0. We also say that x is equal to alpha is a solution of the quadratic equation, or that alpha satisfies the quadratic equation. The zeros of the quadratic polynomial ax square plus bx plus c and the roots of the quadratic equation ax square plus bx plus c is equal to 0 are the same. Solution of a quadratic equation by factorization. Let us learn to find the roots of the equation by factorization. Take an equation x square minus 9x plus 20 as 0. Solution. First, factorize the quadratic equation x square minus 9x plus 20 as 0. Find two numbers which add up to 9 and multiply to give 20. These numbers are 4 and 5. X minus 4 into x minus 5 is equal to 0. Now find the value x so that when these brackets are multiplied together, the answer is 0. This means either x minus 4 is equal to 0 or x minus 5 is equal to 0. So, x is equal to 4 or x is equal to 5. You can check these answers by substituting 4 and 5 into the equation. X square minus 9x plus 20. Substituting 4 gives 4 square minus 9 into 4 plus 20 is equal to 16 minus 36 plus 20 equals 0. Substituting 5 gives 5 square minus 9 into 5 plus 20 is equal to 25 minus 45 plus 20 equals 0. Remember these three simple steps and you will be able to solve quadratic equations. Example. Suppose we wish to solve x square minus 5x plus 6 is equal to 0. We factorize the quadratic by looking for two numbers which multiply together to give 6 and add to give minus 5. Now minus 3 into minus 2 is equal to 6 and minus 3 plus minus 2 is equal to minus 5. So the two numbers are minus 3 and minus 2. We use these two numbers to write minus 5x as minus 3x minus 2x and proceed to factorize as follows. From which x minus 3 is equal to 0 or x minus 2 is equal to 0. So that x is equal to 3 or x is equal to 2. These are the two solutions. Example. Now suppose we wish to solve x square minus 3x minus 2 is equal to 0. We are looking for two numbers which multiply to give minus 2 and add together to give minus 3. Never mind how hard you try, you will not find any such two numbers. So, this equation will not factorize. For this, we need another approach. We will learn that in the next screen. Solution of a quadratic equation by completing the square. This is another way to solve a quadratic equation if the equation will not factorize. It is often convenient to write an algebraic expression as a square plus another term. The other term is found by dividing the coefficient of x by 2 and squaring it. Any quadratic equation can be rearranged so that it can be solved in this way. Have a look at this example. Rewrite x square plus 6x as a square plus another term. The coefficient of x is 6. Dividing 6 by 2 and squaring it gives 9. X square plus 6x is equal to x square plus 6x plus 9 minus 9 equals x plus 3 whole square minus 9. Example. Solve 2x square plus 20x plus 3 is equal to 0. Rewrite 2x square plus 20x plus 3 is equal to 0 to get x square on its own. 2 into x square plus 10x plus 3. The coefficient of x is 10. Divide 10 by 2 and square to get 25 is equal to 2 into x plus 5 whole square minus 25 plus 3 equals 2 into x plus 5 whole square minus 50 plus 3 equals 2 into x plus 5 whole square minus 47. We know that 2x square plus 20x plus 3 can be written as 2 into x plus 5 whole square minus 47. Therefore, we can rewrite the equation as 2 into x plus 5 whole square minus 47 equals 0. 2 into x plus 5 whole square is 47. Now dividing both sides by 2 we get x plus 5 whole square is equal to 23.5. Take the square root of both sides. X plus 5 is equal to square root 23.5 or x plus 5 is equal to minus square root 23.5. X is equal to minus 5 plus square root of 23.5 or x is equal to minus 5 minus square root 23.5. X is equal to minus 0.152. Three significant figures or x is equal to minus 9.85. Three significant figures. Nature of roots. The roots of the equation ax square plus bx plus c is equal to 0 are given by x is equal to minus b plus or minus square root b square minus 4ac whole upon 2a. Here, b minus 4ac determines whether the quadratic equation ax square plus bx plus c is equal to 0 has real roots or not. b square minus 4ac is called the discriminant of the quadratic equation. 1. If b square minus 4ac is greater than 0, then the quadratic equation has two distinct real roots. 2. If b square minus 4ac is equal to 0, then the equation has two equal real roots. And 3. If b square minus 4ac is less than 0, then the equation has no real roots. Example. Suppose we wish to solve x square minus 3x minus 2 is equal to 0. Comparing this with the general form ax square plus bx plus c is equal to 0, we see that a is equal to 1, b is equal to minus 3, and c is equal to minus 2. These values are substituted into the formula. It becomes x is equal to minus b plus or minus square root b square minus 4ac whole upon 2a, which is equal to minus into minus 3 plus or minus square root minus 3 square minus 4 into 1 into minus 2 whole upon 2 into 1. By calculating it, we get 3 plus or minus square root 17 upon 2. These solutions are exact. Did you know? Many people believe that Babylonians were the first to solve quadratic equations. In fact, Brahmagupta, AD 598 to 665, gave an explicit formula to solve a quadratic equation of the form ax square plus bx is equal to c. Summary. Let us summarize what we have learned. A quadratic equation in the variable x is of the form ax square plus bx plus c is equal to 0, where a, b, c are real numbers and a is not equal to 0. A real number alpha is said to be a root of the quadratic equation ax square plus bx plus c equals 0 if a alpha square plus b alpha plus c is equal to 0. The zeros of the quadratic polynomial ax square plus bx plus c and the roots of the quadratic equation ax square plus bx plus c is equal to 0 are the same. If we can factorize ax square plus bx plus c, a is not equal to 0, into a product of two linear factors, then the roots of the quadratic equation ax square plus bx plus c is equal to 0 can be found by equating each factor to 0. A quadratic equation can also be solved by the method of completing the square. Quadratic formula. The roots of a quadratic equation ax square plus bx plus c is equal to 0 are given by minus b plus minus is square root b square minus 4ac whole upon 2a, provided b square minus 4ac is greater than or equal to 0. A quadratic equation ax square plus bx plus c is equal to 0 has 1. Two distinct real roots if b square minus 4ac is greater than 0. 2. Two equal roots, that is, coincident roots if b square minus 4ac is equal to 0, and 3. No real roots if b square minus 4ac is smaller than 0.